In this video we're going to be talking about colligative properties. And so we've covered colligative properties in class, but this is kind of your refresher for colligative properties. We know that in a solution you have two things. You have the solute and the solvent. And together they make up the solution. Well, whenever you put the two things together, it changes the properties of the overall combination. So colligative properties are properties of a solution that change depending upon the number of particles dissolved. So it doesn't matter what the thing you're dissolving is, as much as it matters the number of particles that you're putting into solution. And there's two things that happen because of that, something called boiling point elevation and something called freezing point depression. And then there are some calculations that go along with it, and we'll get to that in just a moment. Okay, so let's see what happens with colligative properties, and we're going to first look at boiling point elevation. Okay, well let's remind ourselves first about what happens when water boils. We know that water is made up of water molecules, like you can see here in this picture, and these water molecules have vapor pressure, and that's the pressure of the water molecules pushing up as they escape. They're moving around in the liquid state. Some of them get enough energy to escape, and they escape. If they're moving around enough, and we have a lot of escaping, we get what we call boiling or evaporation. Boiling is going to occur when the vapor pressure, or the pressure of the particles pushing up, is greater than the pressure of the air pushing down. And so in class one day we were able to boil cold water. And we were able to do that because we removed the air pressure, and so the vapor pressure was great enough that the water began to boil. Normally we heat water so that the particles move faster and it increases their vapor pressure. As soon as the vapor pressure becomes more than the air pressure, the water begins to boil. So when the vapor pressure is greater than the air pressure, water boils. And for pure water, water boils at 100 degrees Celsius. But what happens when we add something to the water? When we add something to the water, those solute particles that you can see here in the kind of reddish orange and purple, they take up space. And so adding a solute decreases the vapor pressure. Basically what it does is it blocks the ability of the water molecules to leave. So we can see here in the first picture, more of them were able to leave, but now these are kind of like linebackers, and so they're preventing the water molecules from escaping. That means that we have to have even more temperature, even more kinetic energy in order for the water molecules to leave. So if the original boiling point was 100 degrees Celsius, by adding solute, our new boiling point might be 103 degrees Celsius. And that's why we call it boiling point elevation. The boiling point is going to go up whenever we add a solute. So adding a solute increases the boiling point, and it increases the boiling point because it is decreasing the vapor pressure. We call that boiling point elevation. Well, if the boiling point goes up, the freezing point goes down. And so let's look at what happens with freezing point depression. In freezing point depression, we're going to look at what a normal ice crystal looks like, and then what happens when we add solute. So let's say that this is a normal ice crystal. We have we have oxygen, and then we have hydrogens attached to it. And whenever water forms ice, it forms this kind of crystal lattice structure, or this ice lattice structure, where they all connect to each other and it gets this solid, rigid form. Well, water is able to do this when the particles slow down enough to make these links. And this happens at 0 degrees Celsius for pure water. What will happen, though, when we add a solute that takes up space? Well, when we add a solute that takes up space, it makes it harder for this crystal lattice to link into place. And so the solute particles block the crystal formation, and that means it has to be even colder in order to be able to freeze. So if normal water freezes at 0 degrees Celsius, by adding a solute, it might be -5 degrees Celsius or -7 degrees Celsius, depending on how much we are adding. We call this freezing point depression. So we know that out of this, the boiling point is going to be elevated, the freezing point is going to be depressed, or going to be lower than normal. And that's because of colligative properties. Now, we talked briefly about the fact that the number of particles is really important in understanding what's going to happen. The number of particles dissolved. And so we're going to take just a moment to talk about ionization. All right. There are two types of solutes. There are electrolytes and there are non-electrolytes. Electrolyte solutes are ionic compounds. Now remember, an ionic is a nonmetal and a metal from opposite ends of the periodic table. A non-electrolyte is a covalent compound. That would be a nonmetal and a nonmetal. They would be on the same side or on the right side of the periodic table. Now here's where it gets really interesting. Ionic compounds ionize or split up in water. That would mean that if I had an NaCl or a sodium chloride, it would split up into Na and Cl, and so that would make 2 particles. So for every 1 NaCl I put in, I would get 2 particles in my solution. Well, let's look at a covalent compound, something like CH3O. Carbon, hydrogen, and oxygen are all nonmetals, so together they make a covalent compound. So when I put CH3O into a solution, it stays as 1 molecule, so it would only count as 1 particle. Well, let's look at CaCl2. CaCl2 is a metal and a nonmetal, and when it splits up, I would get CaClCl, so I would get 3 particles. Glucose is C6H12O6. That, it takes up only 1 particle because it's nonmetals bonded to nonmetals. So the number of particles that it breaks into is called the Van't Hoff factor, and we use lowercase I for that. The higher the Van't Hoff factor means the higher the colligative change that we're going to see. And that's because the more pieces it breaks into, the more blocking of vapor pressure and the more blocking of the crystal lattice it's going to be able to do. So if I wanted to have the greatest impact in boiling point, would I want to use NaCl, CH3O, C6H12O6, or CaCl2? I'd want to use CaCl2, and that's because it would break into 3 particles, so it would have 3 times the blocking power of, say, glucose or CH3O. And that would be because these only take up 1 particle apiece, this one would take up 3 particles, and that's ionization. So just kind of as a refresher, we know that colligative properties are properties of a solution that depend on the number of particles dissolved, and that will do 2 things. It will elevate the boiling point, and it'll depress or lower the freezing point. We know that the boiling point elevates because it's going to decrease the vapor pressure, blocking those water molecules from leaving, and it's going to depress the freezing point because we're going to have to drop the temperature even more to be able to get our water molecules to connect. That is colligative properties.